Okie dokie, partial fractions. Okay, to motivate what we're doing here, I'm going to combine these two fractions into a single fraction. This will all make sense, I promise. Okay, so common denominator will be the product of the two denominators. Now on top you get 2 times this denominator. And then minus 1 times this denominator. Don't forget your brackets. And then when you work this out, you get x, and then 4 plus 1 is 5 over the same denominator. So what was the point of all that? Well, we're going to be given integrals of this form over here. And it's going to be useful to work, backwards and obtain something of this form. So we'll be taking a single fraction and decomposing it into partial fractions. So 2 partial fractions or 3 or more. And we're going to develop a systematic way to go from here to here. So to go from right to left. To go from left to right, that's easy, but right to left is probably something new. Okay, here's my first example, which is actually exactly this guy up here, well, the integral of this guy up here. So I already know how it's going to decompose, but let's go through it to see the systematic method. Okie dokie. So what I want to do is pause and copy if you haven't done so already. What I want to do is kind of propose something and then go and find A and B. Now, it's kind of a theorem of arithmetic that something of this form can be written in this form, but we won't get into the details of that. Okay, so what we'll do first is we will clear all the fractions. So what I'll do is I will take this denominator here and multiply both sides by this denominator. So let's call it star. So I'm going to imagine star ending up here and also ending up here. So what happens when you work it out is you get this first of all. Okay, so again, I'm multiplying both sides by this thing I've circled here. And then there are cancellations. And I get this line here. I'm trying to find A and B. What I'm saying here is that for any x, this rectangled equation is true. So what I can do is just start plugging in x's. I can do so at random, that will also work, but I'm going to make clever choices. So I'm going to go x equals 1. Why did I go x equals 1? Because that will make this term disappear. So if I plug in x equals 1, I get 6 on the left, and then I just get 3b here, and then 0 for the rectangled bit here. And then immediately I have b is equal to 2, so I found b. Okay, so again, to repeat, I chose x equals 1 to make my life easy by killing this term. Okay, next I'll go x is negative 2 to kill this term and thus find a. Okay, so pause and copy if you haven't done so already. So now I found a and b. And my original integral has been transformed into something which is quite easy. And in fact, I will recommend you memorize this formula in green. It comes up often enough that it's worth memorizing. So I'll use this formula here and here, giving me my final answer. Okay, so we have what's called the first case. So this was called distinct linear factors because this x plus 2 is a linear factor, and linear meaning ax plus b, and this is also ax plus b, and they are distinct. X plus 2 is not the same as x minus 1. So you have two distinct linear factors that make up our denominator at the beginning. Let me just scroll up to show you. Where was I? So this original denominator was, when you factor it, a product of distinct linear factors. Okay, and then to handle that situation, here's the pattern that will work. Let me scroll back down for you. So case one, distinct linear factors. Here are two more examples of just the decomposition. If you got three terms or three factors, then you get A, B, C over here, of course. X on its own counts as a linear factor. So X gets its letter along with X plus 1 getting its letter.